Welcome to the Explainer. Today we're going to unpack one of the absolute most fascinating phenomena in the physical world. We're talking about an invisible force that fundamentally shapes motion, completely dictates modern travel, and heavily influences the design of pretty much every fast-moving object you see around you. Honestly, once you understand how this works, it'll completely change how you look at the physical world. It dictates exactly how efficiently we move through the atmosphere and sets the absolute limits on our engineering capabilities. So let's dive right in. Have you ever really stopped to think about how a bird just glides without even flapping its wings? Or how a massively heavy passenger plane, we're talking hundreds of tons of metal here, somehow manages to travel thousands of kilometers without just dropping out of the sky? Or why sports cars have those incredibly smooth sweeping curves that somehow glue them to the asphalt at terrifying speeds? On the surface, it almost looks like they're totally defying gravity and wind resistance. But there's no magic here. The answer to this whole mystery lies in the very precise manipulation of physics, and that is exactly what we're unpacking today. Section 1, the invisible force. So let's get our foundational definition out of the way. Aerodynamics. It is essentially the branch of physics that studies exactly how air interacts with moving objects. And it doesn't matter what the object is, whether it's a massive commercial jet, a Formula One car, a little drone buzzing around your backyard, or literally just a golf ball flying down the fairway, every single object moving through the air experiences aerodynamic forces. The fundamental goal of aerodynamics is basically a constant balancing act. It's this endless battle to reduce resistance, which we call drag, while simultaneously maximizing an object's performance. Sometimes that means cutting through the air as smoothly as possible, and other times it means actively grabbing that air to create essential stability or lift. That's the golden rule we're going to see applied over and over again. Now, to truly wrap our heads around aerodynamics, we have to stop thinking of the air around us as just empty space. It's really not. It actually acts as a highly dynamic, dense, fluid medium. When an aircraft moves forward, it is actively pushing its way through an ocean of invisible particles. And at high speeds, this air behaves almost like a thick liquid, meaning resistance increases exponentially the faster you go. You've got millions and millions of physical air molecules constantly colliding with the surface of the vehicle. And all those countless tiny microscopic interactions, they add up to create massive physical forces that totally dictate performance. This is exactly why engineers have to agonize over every single inch of an airplane, from the precise angle of the nose, across the sweeping curves of the wings, all the way back to the tail. The whole shebang is designed just to manipulate and control that fluid flow.
Section 2, Rules of the R.
Okay, so the absolute most important concept in aerodynamics is airflow, and it generally comes in two distinct flavors. First up, we have laminar flow. This is basically the holy grail for engineers. It happens when air moves incredibly smoothly over a surface in perfect parallel layers. Smooth airflow means far less drag, which makes the aircraft significantly faster and super fuel efficient. But when air moves too abruptly or hits a sharp angle, the flow literally separates from the surface. And that gives us our second flavor, turbulent flow. The air becomes chaotic, swirling around and creating a low-pressure wake that physically pulls the object backward. This dramatic spike in resistance acts almost like a giant invisible parachute dragging behind the object. And you guessed it, that totally ruins efficiency and performance. So how do we actually capture that beautiful laminar flow and stay up in the sky? Well, engineers rely on a brilliant concept known as the airfoil. If you ever look closely out the window at the wing of a passenger plane, you'll notice it is absolutely not flat, not even close. It has a very specially designed curved shape. And that specific curve actually forces the air traveling over the top of the wing to move a lot faster than the air moving underneath it. According to the rules of fluid dynamics, this difference in speed creates an area of low pressure above the wing and higher pressure below it. And that higher pressure actively pushes the entire aircraft up, generating the physical force we know as lift. It's exactly this precise geometry that lets a heavy aircraft straight up beat gravity. Section 3. Beyond just airplanes. Now, this invisible force is shaping way more than just aviation. Take Formula One race cars, for example. They use the exact same aerodynamic principles we just talked about, but instead of using airfoils to create lift and fly away, they literally flip the airfoils upside down. This generates immense downforce, violently pushing the car down into the track. Engineers also use something called ground effect to create low pressure right underneath the car, essentially vacuuming it to the asphalt so they can take corners at insane speeds without flying off into the barriers. Then think about wind turbines. They use highly engineered aerodynamic blades specifically designed to capture the absolute maximum rotational energy from the wind. And, nature definitely did it first. Birds naturally and continuously adjust the exact shape of their wings mid-flight to move efficiently. This actually inspired an entire field of engineering called biomimicry, where we literally steal design secrets from millions of years of natural evolution.
Section 4. Engineering the invisible.
So, how do we actually master these invisible forces and bring a revolutionary machine into reality? Well, it takes a really rigorous, iterative, three-step engineering loop. Step 1 is the shape design. This is where engineers first conceptualize the basic airfoils and curves based on the fundamental physics of lift and drag. Step 2 is digital simulation, bringing those exact shapes into incredibly advanced computing environments to mathematically test the airflow. And finally, step 3 is physical testing, where they put real physical scale models into moving air to make sure the math actually checks out. It's just a continuous, relentless cycle of designing, testing, and refining. Let's actually zoom in on those last two steps for a second, because the technology driving them is absolutely mind-blowing. Step 2 relies heavily on computational fluid dynamics, or CFD for short. Today's aerospace engineers use absolute beastly supercomputers to study airflow way before anyone even thinks about cutting a single piece of metal. With CFD, they can entirely simulate how air will move around an aircraft in a completely digital space. We're talking computers solving millions of complex fluid equations every single second. This allows engineers to safely test how a design is going to handle extreme weather, massive temperature shifts, or radical speeds, all without risking a single human life. These advanced simulations save massive amounts of time, they drastically slash development costs, and they critically improve the structural safety of the aircraft long before manufacturing even begins. It's a total game changer. But hey, even with all that incredible digital simulation power, aircraft are still heavily tested inside physical wind tunnels for Step 3. These things are massive facilities, equipped with incredibly powerful fans that create highly controlled, continuous streams of air. Inside, engineers can directly observe how actual air moves around real, physical scale models. And to make this invisible force visible, they'll inject really precise smoke streams right into the tunnel, or they'll paint the models with special UV fluorescent dyes. This lets them accurately track the exact path of the air over the surface. They go on a very systematic hunt, looking for any areas where the air separates and becomes chaotic. Once they spot those specific points of high drag, they can physically tweak and perfect the geometry. Section 5. The future of flight. Okay, so what's next? Because as technology marches forward, aerodynamics is rapidly evolving. Right now, researchers are actively developing completely new, radical shapes for aircraft, like blended wing bodies. See, traditional airplanes suffer from a lot of drag right at the joint where the wing meets the main body. But a blended wing eliminates that joint entirely. It makes the whole craft act as one giant continuous airfoil that lifts itself. We're also seeing the rise of adaptive wings. Thanks to advanced materials, these wings can literally change their physical shape mid-flight to optimize for different speeds and altitudes. It's perfect biomimicry, just like a bird seamlessly adjusting its feathers. And, perhaps the wildest part of all, engineers are fundamentally rewriting the rulebook to create hypersonic vehicles. When we say hypersonic, we're talking Mach 5. That is more than 5 times the speed of sound. At those extreme velocities, the aerodynamic challenges just completely shift. Pushing a vehicle through the atmosphere that fast generates an unbelievable amount of friction. The air molecules violently compress against the nose and the leading edges of the craft, creating a blanket of heat so intense it can literally melt traditional metals. Solving for this extreme thermal barrier, while somehow still maintaining a stable flight path, is for sure one of the greatest hurdles in modern aerospace engineering today. Now, you might be asking yourself, so what? Why does all this complex engineering actually matter to me? Well, because every single incremental improvement in aerodynamics leads to tangible, everyday benefits. Better aerodynamics obviously means significantly faster travel times and a much smoother ride. But way more importantly, it means substantially lower fuel consumption. Aerodynamics isn't just a tool for going fast, it's a massive weapon in fighting climate change. By maximizing fuel efficiency and minimizing drag, we heavily reduce carbon emissions. It paves the way for a much greener future in global transport. And at the end of the day, mastering these rules of the air just results in vastly safer, much more stable aircraft for all of us. When you really step back and look at the big picture here, aerodynamics is so much more than just numbers and physics equations. Every single airplane crossing the sky above you right now is a powerful, flying reminder of human ingenuity. Understanding something as seemingly simple and mundane as moving air, it allowed humanity to achieve one of its absolute greatest historical dreams, the dream of flight. It completely redefined our physical boundaries and literally shrank the globe. It really is the invisible force that shapes how we fly, how we travel across the world, how we compete on the racetrack, and how we explore the skies. So the next time you put your hand out the window of a moving car and feel the wind pushing back, or you see a bird just effortlessly gliding past, I hope you remember the incredibly complex, invisible ocean we all live in. As we push closer and closer toward everyday hypersonic travel and advanced biomimicry, it begs the ultimate question. If understanding moving air took us from the dirt to the very edge of space in just 1 century, what on earth is the next century of manipulating this invisible force going to look like? Thanks for joining me on this explainer, and stay curious.